Hello, Squidlings. We're meeting with Alona again, my friend from Los Angeles. You'll notice that I'm a little bit on one side of the screen, and that's because I have a secret to show you. I want to show you a new friend that I've got. Oh, oh.
Oh my god!
His name is Shiva. A couple
Like
people around here.
Indian,
Oh, there you go. See you, Mr. Shiva. A couple
like a
people point out
Hindu
that he
god.
yeah, he has a mark on his forehead that looks sort of like a third eye. So his name is Shiva, Shiva the Destroyer. But I'll be honest, I usually just call him Mr. Cat.
Oh, that's the cutest
Uh,
being. I love that. Okay, is he gonna be giving the lecture for us today?
uh, I'd like that. He's taught me a lot. And then another interesting surprise I want to show people. I made this shirt. I made a video about me having a seizure, and it turns out I have closed lip schizencephaly. But I didn't show my MRI. I wanted some privacy, but I don't really want that privacy. I think I have a really interesting looking MRI. So this part of my brain looks pretty normal, but then on the other side, there's this interesting
It's
like
Shiva's brains.
yeah. So it's all right. So I just wanted to just wanted to show that off, I suppose. I'd like to present a little something something. I think I've been telling a lot of people that I'm publishing a paper about applying Carl Friston's free energy principle to reinforcement learning. So in our last meeting, we talked a lot about reinforcement learning. So I think when I make a video about the paper that I'm publishing, I'll definitely link the video that we made together before. But I actually just contacted the people publishing my paper. I thought they would be publishing it like within a month. They're not going to be actually publishing it until October. Oh, and I really want to talk about it, but I'm not supposed to talk about it until it's actually out. Actually, Neural Computation, the journal that's publishing it, says that because they're publishing it, I can just put it on archive. So that video is going to come up. But this paper was incredibly important to me actually writing that paper. So how about we talk about this one? A curiosity algorithm for robots based on the free energy principle. I remember in our last meeting, you were less interested in the technical side of reinforcement learning because it didn't seem terribly interesting.
I yes, you just have a professor personality about you. You go on and on about things that I'm sure are interesting, but it's okay to have a professor personality. Yeah, I think I'm just like I was curious in implications and overall like progression, but I didn't like go into formulas as you usually go into that.
Well, I hope that this one will be a little more interesting. And thank you for saying that I have a professor-like personality. I guess maybe I've developed that just being a PhD here and sometimes teaching classes. So let's work on this paper. Hoo boy. So here's the abstract, and we don't need to read the entire abstract. I'm just going to summarize it. I've got a little summary. So reinforcement learning. It's one of the most commonly used algorithms for robotic task learning, which we learned about last time. So we had the most boring tasks imaginable, where there's like a pole, and the pole was falling, and we could choose to move left or right, which is pretty boring. I think we're going to do something slightly more interesting. But in the last video, we also talked about random exploration. When we played those games, we just started the robot making random actions so that it could understand what the context is, what it's doing. But that's not very good at it. Random actions, it's not very efficient, especially when you're using something which has high-dimensional continuous action space, as opposed to the binary action space of just pushing left or pushing right. So in order to make the robot curious, let's make it related to the free energy principle. And also use the soft actor critic, which we also talked about last time, where the agent is sort of controlling its randomness. So, with a little summary, in reinforcement learning, RL, robots must explore to find information so that they can exploit that information. They can't exploit something until they learn about it. And random actions, that's not going to work. So we're supposed to use entropy and curiosity. The issue is, how do we make curiosity? What is curiosity? We talked about entropy last time, but what is curiosity here? So I hope that this this simulation is a lot more interesting to you than having a pole elevated. We have a robot hand. It has 3 fingers, but I think they're only using the bottom 2 fingers in this case. And it has 3 balls on the robot hand. And so their goal, it's being trained to drop the balls one at a time in regular intervals. So it's not allowed to drop all 3 balls at once. That would just be really easy to do. And they say that this could be relevant in something like cooking. Is that more interesting than a poll?
Definitely, yeah. I did have a lot of questions about this one. So, in order to drop 1 regular intervals, do you mean that the robot has to kind of experimentally find out what degree of like putting the arms down he should do in order to put just 1 ball to drop?
Yeah. So it's a physics simulation, and at the very end of this, we're going to see that it works not only in simulation but with an actual physical robot. So in this case, it really is just trying to figure out how much it needs to drop both of its 2 hands in order for 1 ball to fall while the other 2 balls manage to cling to the robot's hand. So that's a lot more complicated than the pole, especially because it has continuous action, which means that's random exploration isn't going to work. So let's get into the free energy principle. And we have a lot of text on one side, but I have a little summary down on the other side. So we're talking about Bayesian inference, Bayesian statistics, which is, according to Carl Friston, sort of the way that we perceive reality. We perceive reality as a probability distribution where there are some things we're really certain about and there are some things that we're not really certain about. So in summary of this, prior distribution is easy to find. The prior probability distribution, like a px, that's the way that things are, if I understand correctly. But then there's also posterior distribution, which means that when we get information, that changes what we know about reality. So when we get data, D, that changes what we think about X. It changes our probability of thinking about X. And this is really hard to calculate because it involves an integral here. So on the next page, we'll do like a really simple version of this where we don't need an integral, but if the data is high dimensional and continuous, maybe we can't do that integral, which means that for the free energy principle in reinforcement learning, we're going to need to estimate the posterior distribution. So any thoughts on this page? I think I saw you writing some things, so.
So I was actually writing a part of the Bayesian statistics where Kristen is sure of the fact that Bayesian statistic is always human perceived reality. I think we can discuss more of that during my part, which is going to be a bit philosophical.
Oh, perfect, actually, yeah. I like that then, we have like a technical side on my end and then a more philosophical side on your end.
Yeah, and then for the formula, so are we dividing the product of posterior distribution and prior distribution to the area of like the whole distribution? Like since integral, it's like a square footage of the function, right? So we have a function, that's just kind of how I was imagining it, but maybe I'm just like wrong. If you have like a function that's over here that represents the distribution of like prediction. So then the integral would be this whole area, right? And then you're taking a product posterior and prior and then dividing by area. Is that how this?
It might help if I go to the next slide where I have an example. So this isn't in the paper that we're talking about, but I think it's important to have an example. Let's suppose that 1% of people have COVID. And let's suppose that we have a test which is 90% accurate at determining whether or not you have COVID or not. You know, you've tested positive, and that's some data. We're getting some data here. What's the probability that we actually have COVID? The prior here, the value of x. Do you want to make a guess? I did share these slides with you before, but do you want to make a guess about what's the probability you have COVID when you test positive for it?
Right. In that, yeah, you did slides. I don't have a like exact memory, but what's the probability I have COVID considering I did test?
Yeah,
Positive?
you tested
Oh, okay.
positive. So do you have COVID?
Okay.
What's the probability you've got COVID?
I tested positive, so it's 0.9 that I need to multiply by 0.1.
I think that's a good guess. So if we do the incredibly technical stuff, we're going to start with the probability of testing positive, regardless of whether or not we have COVID. So if we do have COVID, if the value of x is yes, we do have COVID, well, the probability that we get this positive test times the probability that we have COVID is one part. That's the probability of having a positive test if we do have COVID. But then we also have to add the probability that we're going to get a positive test if we don't have COVID, times the probability of not having COVID. So on the next part, I include the numbers here. So it's a 90% probability times a 1% probability, plus a 10% probability times a 99% probability, which means that regardless of whether or not we have COVID, whether we have COVID or we don't have COVID, we've got roughly a 11% probability of testing positive for COVID.
But I see now, like I did forget, so we have to also add the case where I didn't. What is 0.1 is a 9/10. Oh, where the test is not accurate, and then the 0.99 is that I don't have COVID.
Yeah. So there's
Why
this.
am I adding a case where
Well,
I don't?
maybe you don't have COVID, but it's still possible to test positive.
But then why am I adding it, not subtracting?
Well, because we're trying to figure out the probability of having a positive test in total. So maybe you do have COVID, and then we have this probability, or maybe you don't have COVID, and then we have this probability. So regardless of whether or not we have COVID, we could get a positive test.
Right.
So if we go to the Bayesian theorem, what's the probability that we have COVID given the fact that we've tested positive? Well, that's the probability that we test positive given that we do have COVID times the probability of having COVID divided by the probability of testing positive, which we just calculated. Maybe we test positive because we do have COVID. Maybe we tested positive because we don't have COVID, but the test was wrong. And so if we plug in the numbers here, it looks like we have about an 8% chance of having COVID, which means that if we test positive, we still probably don't have COVID. If the probability of not having COVID and still getting a positive test is so much higher than having COVID and getting a positive test. So in this abstract simulation, testing positive only means a 8% chance of actually having COVID, which means we have to, take more tests. It helps to actually get multiple tests for this sort of thing. The issue regarding the free energy principle is that in this case, there are only two cases. Either you have COVID or you don't. In reality, when we talk about our perception of reality, there are so many different cases, so many different things that can happen, and they're continuous, which means we have to have that integral, and that integral might not be actually calculable.
That's a great example. Definitely helped me to grasp the concept better. You said the integral is not going to be calculable?
Yeah, if I go back to the previous slide, this integral here, when we're talking about continuous data that we can get and continuous prior states, continuous possibilities, we have to calculate this value for every possible kind of data and every possible kind of outcome, which it might not actually be something that we can calculate. Or if we can calculate it, it's absurdly computationally expensive. So
I see.
I believe the way we get around this on the next page is by making an estimation of what that value is. You know, we can't actually get the value, but we can estimate it. And the way that we can estimate it involves Kolbeck-Leibler divergence. So Kolbeck-Leibler divergence is how we can compare probability distributions. And I'll be honest, this is complicated. This is more complicated for me to completely understand. And in fact, this thing that we're looking at right now, this is only Kolbeck-Leibler divergence when we're talking about Gaussian distributions. So when we're talking about just stuff like a bell curve. If we're talking about different kinds of probability distributions, I think this equation is completely different. And so in the future, I'm just going to call this DKL, or a KL divergence. So we're going to see that if we have this estimation, where we're estimating this value based only on the value of x instead of, so we're trying to guess how d impacts this, then we're going to have this integral, which is actually something we might be able to solve. And it just so happens that this f value is the free energy. The free energy principle says that the goal is minimizing this f value, the free energy, which means that we're trying to make accurate predictions based on a stable worldview. We don't want our worldview to be constantly shifting back and forth whenever we get data. If we get data and our worldview completely changes every time, that's not a very stable worldview. We want a worldview which is comprehensive enough, it understands reality enough that we can make accurate predictions in a consistent way. So I believe this is another slightly technical side. They make a transition model, which means that it's a neural network which is given a state and an action, and it uses the state and the action to predict the next state. So given all the data we've got and what we're doing, we're trying to predict what the future will be like. They call it a transitioner. There are a lot of words for it. It can be the transitioner. It can be a world model because it represents our conceptualization of the world. I usually call it a forward model because we're predicting what's going to happen when we go forward in time. They specifically make it a Bayesian neural network, which means it doesn't have weights. It doesn't have parameters. So in a neural network, you have weights, you have numbers that you're multiplying. But instead of having those numbers, we have probability distributions. And when we use the Bayesian neural network, we sample what weights we're going to be using. So maybe there are some parts of the network that we're really sure of. There's low variance, which means we'll be taking the same weights every time. But sometimes we're completely unsure of something, which means there's high variance, which means the weights might be all over the place when we sample them. So we're using a transitioner, aka a whole bunch of other names, as a BNN, a Bayesian neural network, which is trying to stably predict the next state in a way which minimizes free energy. because it's trying to make accurate predictions, but it also wants the probability distributions that it's using to be stable. So curiosity is the DKL, the divergence, when we compare those probability distributions before and after training with a state. So if we have the forward model at one point, and then we get in a new state, and we train the model to say, well, now that you've made this prediction, and it was right in these ways, and it was wrong in these ways, how do you change that probability model? Are you less sure about some things? Are you more sure about some things? And the higher the divergence, the more the model has changed, that's a curiosity value.
I saw there was that you point out a couple of slides before that the model is interested in creating the worldview that is stable enough. Yet every time so now with this sort of algorithm, it's interested in the case where the model before and model after have basically large discrepancies. So how does that coexist, and what's the balance between having a stable enough model versus being interested in the cases which have large discrepancies between what's predicted and what's predicted, or what's observed or predicted after their event?
That is a perfect question. I think I might answer that on the next slide, but that is a great question. Like I said, the forward model, it wants to minimize free energy, which means it wants like the probability distributions before and after to be really stable. Like when it gets a new state, it's supposed to say, okay, yeah, I expected that state. I predicted it accurately, and it's not changing my view of the world. You know, it makes sense. But then also, I'm saying that the curiosity value, I mean, we're trying to maximize curiosity. We care about curiosity. We want curiosity, which means that we also want the probability distributions to be completely different. How does that work? But just before that, they're also using a soft actor critic, which we talked about last time. It means that the agent is sort of choosing how random its actions are. So sometimes it'll do something really random just to see if it can find something new. So the soft actor critic provides entropy. So let's see. We already talked about free energy. There's another thing called expected free energy. And expected free energy involves curiosity, which we just talked about. So that's our view of the world, the way that we predict things before training and after training, plus the reward we got, plus something for entropy, and something for imitation. We're not going to use imitation. Imitation is cheating. Imitation means that we give the model the correct answer, like the correct action, and then it's supposed to, it'll be rewarded if it guesses that correct action. So that's cheating. Come on. So the transformer wants to minimize free energy, but the actor is rewarded for maximizing expected free energy. And this blows my mind. The transitioner and the actor, the forward model and the actor, have an adversarial relationship where the forward model wants to minimize free energy, but the actor is rewarded for maximizing it, which means the forward model, it's trying to like make a consistent worldview and make accurate predictions. It's trying to understand the universe. And then the actor is like, you missed a spot.
It kind of blows my mind too now that you're explaining it.
Yeah. So I guess in reality, we want to have a consistent worldview. We want to know how the world works around us. But the way we do that is by investigating everything and finding things that completely change our worldview. So if we have a box and we don't know what's in the box, we want to open the box. We want to see what's in there.
Put the gun
I
down.
saw you with the box. What was in the box? Oh, what's in the box?
And that might completely change our worldview. But because it changes our worldview, we might have a stable worldview after that. Oh, I can't remember the name of this director or scriptwriter who said that in all of his stuff, the TV show Lost and Cloverfield, and he said that, oh, you got to always have a box in your writing, and you're not allowed to open the box. Don't open the box, which is kind of why Lost and Cloverfield, I'm not a big fan of them, because there's nothing in the box. And I think the readers, they are interested in the box, but they want to know what's in the box. Eventually, you have to show them what's in the box.
The thing is that it represents infinite possibility. It represents hope. It represents potential. And I realized that mystery is the catalyst for imagination. Now, it's not the most groundbreaking idea, but when I started to think that maybe there are times when mystery is more important than knowledge, I started getting interested in this. The mystery box, in honor of my grandfather, stays closed. Thank you.
Interesting. It's like Tarantino's movie where they had a suitcase. What is the name of it?
Yeah. It's not Reservoir Dogs, and it's like there's a suitcase, and the suitcase is like a
Fiction.
Pulp Fiction. Pulp Fiction. So in Pulp Fiction, they have like a suitcase. And what's in the suitcase is like, the suitcase is so important. It's like driving the plot, but you never see what's in the suitcase. They just have like a light that turns on when they open the suitcase, and so it lights up the actor's face, but you're not allowed to see it. And I think that works. You know, I think it leads in interesting places. So I think we're almost done. Okay, we don't have to spend a whole lot of time on this page. This page is nothing but technical stuff. We can see here's the transitioner. It gets a state, it gets an action, and from this we get a curiosity value, which we talked about on the last page. There's a policy, which is what we're calling an actor, gets a state, it makes an action. We've got a value network that we call the critic. It's making a loss function. The actor is trying to impress the critic and get something which the critic says is valuable. And the actor is rewarded for absolutely confusing the transitioner. And on the other side, we have pseudocode, which I think we might as well just skip. In the beginning, you make the neural networks, that's how you start. And then in every episode, like every time the robot is given a task and it's just starting from scratch and it has to figure stuff out, every step of that, it'll make an action, it'll perform the action and find a reward and a new state. We calculate free energy, and we use that to train the transitioner. But then we also get the real reward value, which includes entropy and curiosity. We store stuff in a replay buffer so we can get it later and use it to train stuff, and then we use it to train stuff. We train a critic and an actor, and we have a target critic. We don't have to talk about that. So do you have any comments on this absurdly technical page? I
mean, the specific implementation, the pseudocode, I don't have enough cocktail for that one, but the part where you were discussing that actor is trying to impress critic by confusing transitioner is actually very, very interesting to me. So I think it's extremely sophisticated algorithm that is like trying to probably mimic how we function as human beings.
Absolutely.
So I want to discuss more of that, but
I think it might be better for us to get deeper into that on your side. Also, Squidlings, go check out Dork Matter Girl, Aleona's channel, where we're gonna have the other side of this conversation. And so I think you're absolutely right that Carl Friston is a neuroscientist. He made the free energy principle about biological agents. And so the fact that we can make robots which sort of behave like biological agents. That's so cool. So now we can finish up. So the results in a simulation. Look, here's the robot hand we saw in the beginning. And so this blue line represents how accurate, how well the robot was doing from epoch to epoch, like it's training from left to right, and it got pretty good. But even better is using the soft actor critic and curiosity, their definition of curiosity, which is the orange one. It doesn't look like it's doing that much better, but it's doing better. And also on the next slide, oh, well, what do you know? We don't just have to do it in simulation. It works in real life. They have a physical copy of the robot. So I'm pretty sure they trained it in the simulation, but then they put it in the real robot. And this is kind of small, but you can see over here, this is like filming it from the side. So it has 3 balls, and it's moving its fingers just a little bit, and it looks like it's lowering one of the fingers, but not the other one, and it drops a ball, and now it's raising the fingers again, and it eventually drops a second ball, and then near the end, it drops the 3rd ball. Ooh, it did it. And apparently, given the results, the way that it does it better is when it's sort of wondering not just how to get rewards for dropping the balls, but also trying to figure out how the whole situation works by experimenting without caring about the reward. So it does care about the reward, but it also cares about abstract stuff, more unrelated things. And because it investigates those unrelated things, it can get better rewards. So
did you conduct experiments for your paper as well, or could you verify it on the physical robot?
Not on a physical robot. I worked entirely with simulated robots, which I think some people might be disappointed by. But in theory, I could do it with physical robots. I think the task that I give it, which I'm not going to disclose, it could actually be done with a physical robot. So in conclusion, curiosity and entropy directly derived from the free energy principle. Entropy is also derived from the free energy principle, by the way. I'm sure that it started as something unrelated to the free energy principle, but you can directly derive it from the free energy principle. It helps robots explore to find information they can exploit. Is this the best way to do it? I mean, Bayesian neural networks, they're computationally expensive to use. And in order to, well, usually in neural networks, you train with batches of data all at once. So in this case, we trained the actor and the critic using batches of data, whole collections of data, but we train the forward model only based on one state at a time. Because in order to get that curiosity value, we need to train with just one step, which is computationally exhausting. In order to get the curiosity value, you have to see the model before and after training, one state, which means that you can't really use a whole batch of data, because if you used a whole batch of data, you would only get one curiosity value. You'd get a before the training and an after the training, but you couldn't relate that to any individual state. It's just like all the states. I'm pretty sure I understand this. I think I think I'm reporting this correctly.
I was wondering if there's a possibility of having another model that the function of that model is to observe this model after every step. So instead of you training the model state at a time, another model is training this model one state at a time, so you don't have to look at the result.
Maybe. Well, can we do something better? Well, you'll have to watch my next video and find out. Except, actually, that's what I wanted to say, but my paper is being published in October, which means it'll be a few more months before I'm actually allowed to make that video. No, I think I should be able to make that video, maybe next month, maybe the month after that.
What else could have you implemented there Maybe you have some average value. Maybe you train it like a bat at a time and then look at the average. And
I did try implementing that, but it didn't work terribly well for me, I'm afraid. But I'll say, I think I can spoil this much. In the paper that I wrote, and which will be published in Neural Computation, I describe a way to use entire batches of data at once for the forward model and still get curiosity values for every single one of the states which was used. And so that's pretty cool. So that's the end of my presentation. Here, so
Sweet, super exciting. I'm very excited for your paper to come out, and thank you for sharing it's a teaser or a trailer for us. So
yeah, do you have any other questions after all that you or would maybe you'd rather ask them on your side?
Yeah, let's do that. I have plenty of questions here for you, and I think it will cover the most of your presentation.
All right, so Squidlings, go to Dork Matter Girl's channel. I think we'll have a really interesting conversation over there.
Thank you. Okay, give me like 3 minutes, okay?
Sure. By the way, I've got a Patreon at patreon.com/Thinkster. I want to thank all these Squidlings and Elder Squids. Thanks.